All right, today I want to talk about conservation momentum, and I want to start with reminding you that last time we talked about impulse momentum theorem and how it was based on Newton's second law. Impulse momentum theorem was that a change in momentum, delta P, is equal to impulse, right? And so that led to delta P equals F times delta T. And we could go further along that road. We did that last time and derive that formula some more. But this time, conservation momentum is based on Newton's third law, which Newton's third stated that for every action there was an equal and opposite reaction. Forces equal and opposite occur on different objects. And are simultaneous. Okay, ran out of room there, so. All right, so that's just a reminder of what Newton's third states. Okay. So down here we have a collision between objects 1 and 2. And what we see is that that the force on, let me see if I can, force on object 2, right, which we'll call F, the force of 1 on 2, right, is equal and opposite then to the force of 2 on 1, right? That this is a Newton's third law pair. Both forces equal and opposite occurring on different objects. And that's what we have there. So we can also state this as F2 on 1 is equal to negative F1 on 2. How does that, that's kind of tough to think about, but I guess you can think about it, say, if this force right here of 1 on 2, which points right, is positive 10 newtons, and then this force right here would be negative 10 newtons of F2 on 1. So the force on object 1 is to the left and negative, and the force on object 2 is to the right and positive. And if that's the case, then we can come down here and plug these numbers in to this equation. So we could say negative 10 newtons, which is F2 on 1, is equal then to a negative of the positive 10 newtons, which is F1 on 2. And that's what that equation right there is trying to state, which is true, right? Negative 10 newtons does equal negative 10 newtons if we do the math there. Since impulse is J equals F times T, right? So we just would take our negative 10 and multiply it by a time, like a couple seconds or 100 milliseconds, or take your positive 10 and multiply it by a time. So what I'm trying to say here is that impulse is going to have a sign then, right? And because of that, we can state the same, because they have the same, impulse has the same force value, right? We can state, instead of saying F2 on 1 equals negative F1 on 2, we can also state J1, right, which is the impulse on object 1, right, is equal to the negative of the impulse on object 2. And because impulse is the same as change in momentum, we can then say that the change in momentum on object 1, right, which is receiving the negative 10 force, is equal to the negative of the change in momentum on object 2, which is receiving the positive 10 force. And by the same logic, by the same math that I showed above. And so what this states then is if object 1's momentum increases by, say, by negative 100 kilogram, let's say object 1 increases its momentum by negative 100 kilogram meters per second, then object 2 will increase its momentum by positive 100 kilogram meters per second. And so in this way, momentum is conserved. Now, this does not mean that the total momentum is equal ahead of time. So, for instance, if a couple objects, we see this written as PI equals PF, I have PF equals PI. But what I'm trying to say is if the initial momentum is, say, positive 30 kilogram meters per second of both objects. So meaning both objects have some momentum, but the object maybe moving right is contributing more. That the final momentum, if the forces are equal and opposite, will be positive 30 kilogram meters per second. So I think sometimes when people hear PI equals PF or PF equals PI, it doesn't matter which way you say it, that they think 0 equals 0, but that's not necessarily the case, right? You can start with some positive momentum and end with positive momentum. And because the objects in the collision experience, maybe one of them experiences, right, by colliding, experiences a negative 100 kilogram meters per second in the final, right? But the other one also experiences a positive 100 kilogram meters per second, and therefore you started with 30, right, and end with positive 30. If that makes sense. Like, so yeah. So the momentum is conserved because the gain and the loss, or the gain positive and the gain negative of that, of that 100 that I was just talking about, right? These 100s, they don't change the total, which that total was the 30, right? And because they cancel each other out, right? So it's still, the system still has 30 in the end. Yeah. So I didn't want you getting this idea that because momentum is conserved, there had to be 0 initial and there had to be 0 final. That's not what it's saying. It's just saying the changes, right? The delta P's are going to be equal and opposite. They are going to cancel. So you can also write, because I was just going to say that the hundreds are delta P's and the 30s are momentums, are P. This is delta for the hundreds, and the 30s are just momentum. That's different. One is a change and one is how much momentum it has. Those are different in concept and in quality, so they're not the same. Anyways, hopefully that's making sense. If not, I think it'll make sense more that we do some problems. I just want to show you this down here. So let me think of how I want to write this. I guess I just want to point this out, that PI equals PF, and maybe, I guess I have some room here. PI equals PF can be expanded, right, into P1, object 1, initial, plus the momentum of object 2, initial, is equal to the momentum of object 1, final, plus the momentum of object 2, final. So another way of writing that would be M V1 initial plus M V2 initial is equal to M V1 final plus M V2 final. All right. So what I also want to point out now is that this conservation of momentum that I just wrote 3 different ways here, right, could also, and we're going to see this in the lab here shortly, is that you can also think of it only as happening in the x direction, or only happening in the y direction. So, so what I'm trying to say is you can write your momentum conservation kind of similar to our kinematics formulas, where we write them all in the x direction or all in the y direction. And so you can write Pix equals Pfx, right? And it's a lot like projectile motion, right? Where you can talk about momentum in just the x direction, momentum in the y direction, or total momentum by adding x and y directions together using Pythagorean theorem. So so that's kind of where this is heading, right? So that should remind you of last year when we broke down those vectors into x and y components. We can, well, momentum is a vector. We can break it down to x and y components. So we have P1I, and I guess I was going to put another x here. I guess I probably should have wrote it in between. I'm going to fix that, get rid of that. Okay, so P1xi, P2xi, P1xf, P2xf, M1v1x initial, M2v2x initial, whoops, I forgot some 1s and 2s there. Just realized that. Let's add those in before I go further. Where's black? Okay. So this should have been M1. This should have been M2. This should have been M1. This should have been M2. And I'm going to go back now and flip it and add the red X's now and finish that off. So on the final side, M1 V1 X final, M2 V2 X final. And you could rewrite the whole thing again in the y direction. All right. Is momentum always conserved? The answer is yes, but it depends on the system. And this is kind of a tricky topic, because on the AP test, they could ask, well, show these two objects collide, prove that momentum is conserved, prove that momentum is not conserved in the same problem. And that's kind of a tricky idea. You're like, wait, momentum's always conserved. And it is, but you have to understand what they're getting at there. And that's the idea of systems, meaning momentum is conserved if you make the system large enough. If the system is too small, you will see momentum not being conserved. And I'm going to prove that with the examples down here. So is momentum always conserved? Yes, but it depends on the system. What's a system? A system is a set of particles that are interacting components considered to be a distinct physical entity for the purpose of study. So we like to set up a system. If you remember last year, we would draw these, let me see here. We would draw these dotted lines, right, around something like I'm doing right now around the definition of system. And we would indicate that this is the system of study, and anything inside the system we would say would be internal to the system, for instance, an internal force, and anything outside the system would be an external force. So that's kind of where that's coming from, meaning was it inside the dotted line, or was it outside? Was it coming from outside the dotted line, the force? Obviously, the force was affecting something inside the dotted line, but where is the force coming from? And that's what we were kind of focusing on there. Internal forces don't change the moment. This is really important right here. Let me get that highlighter back. So internal forces don't change the momentum of a system. So the objects, so that the total momentum of the system is always conserved by internal forces. So whatever happens inside the system, it does not affect things, right? That's really a key idea to understanding systems, and that our conservation laws hold when the forces all occur from objects acting on each other that are in the system. But as soon as you have something outside the system, what could be a force outside the system? gravity, right? The Earth is pulling on me from outside the system, if the Earth is out of the system. And then therefore force gravity is an external force. But if we put the Earth in the system, then it would be an internal force. So external forces can change the momentum of a system. And you might say, well, how is the law of conservation of momentum true then if external forces can break it? Well, the idea is if you make your system large enough, for instance, the universe is your system, then you see that all forces are internal. And then therefore the law of conservation of momentum holds for the universe, right? So it's only when we make our system smaller that we start to maybe run into trouble and have the law of conservation of momentum not hold up. But remember what's true for the AP test, that for every collision, momentum is conserved. It's only a problem when we draw our system too small, and that's when it's not conserved. Okay, so momentum, I wrote down here, momentum is conserved when there are no external forces or the sum of the external forces is zero. So for instance, maybe you have force gravity and force normal both occurring from outside the system. Maybe the table that the book is sitting on is outside the system. Then normal would be an external force. And if so let me draw that real quick. So if you had a book resting on a table and the system was just the book. Oh, dang. Let's see if I can do that again. I'll just stick with black. It seems to be working. The system is just this book. And therefore, if I do the free body diagram on this book, let's get some, we have force normal from, which is the force of the table pushing back on the book. It would be external. Whoops, trying to write. And we would have force gravity also being external. But there would be no, we wouldn't have to worry about these external forces because they cancel each other, right? Because they are equal and opposite. Now, they are not a Newton's third law pair because they act on the same object, right? Newton's third law forces have to act on different objects. So anyways, I just wanted to point that out. So momentum is conserved when, right? We said up here, there are no external forces or the sum of the external forces on the object is zero. Then that's when momentum is conserved. All right, an isolated system is a system with no external forces acting on it that can change its momentum. So sometimes you might hear that term, isolated system. Conservation momentum is a law of the universe and is always true if we draw the system large enough. If the system is very small, one object, we see that the one object is an example of when you're drawing it too small, we see that momentum is not conserved. And so we usually try to draw the system large enough so that this doesn't happen, right? Because we like writing our conservation of momentum formulas. There was something else I wanted to add here. Let's go back for a second now to the momentum impulse theorem, right? Which stated that F delta T is equal to delta P, right? And we proved that last time that this came from, you should know which of Newton's laws came from second law, right? This was a form, just another form of writing F equals ma. And see the last lecture for why that's true. All right, so anyhow, something to note here that's pretty cool that you can rewrite this, right? And see something kind of neat. All right, so just expanding it out a little bit. And we can say then, if there are no external forces, right? If there are no external forces, check this out. Get my red marker, then this F is equal to 0. And therefore, 0 times delta T is just 0. Hopefully you see where this is going. Oh, kick PI over to the other side, right? Aha. All right, so when there are no external forces, momentum is conserved. All right, and that's if there are no external forces. And now you see mathematically why, right? Backing up the theory, which we just talked about. Okay. I'm going to pause it right there and come back and do these examples. Okay, so we're going to continue our lecture here with some example problems. And the first one is example 9.5. It says 2 ice skaters, Sandra and David, stand facing each other on frictionless ice. And Sandra has a mass of 45 kilograms and David a mass of 80. They then push off of each other. All right, so let's go ahead and draw this. I'm thinking it's going to look something like this. Let's see. Okay, try and draw David here. This is going to be interesting. And Sandra. Okay, so I'm thinking something like this. They're on ice skates, and it's not a very good drawing, but oh well. All right, so so the system here, let's point this out, is Sandra plus David. So there are no external forces, so therefore we know momentum is going to be conserved. All right, because external forces will change the momentum or lead to an impulse, and that's not what's going to happen here. All right, so initially, mass of David, let's just write this down, is going to equal 80 kilograms. Guess I could have just called that MD. And then the mass of Sandra is going to equal 45 kilograms. V Sandra initial is going to be 0. And V David initial is 0 as well. Then they push off of each other. And it says after the push, Sandra moves at a speed of 2.2 meters per second. So since they're pushing, Sandra is going to go to the right, so her velocity will be positive 2.2. And David will go to the left. Whoops. Probably draw those on the other side. So David's going to be traveling to the left. Let me see if I can draw this. All right. And Sandra will be going to the right. All right. I feel like I'm spending most of my time just drawing right now, not even doing physics. So once again, system is both of them. We're not worried about any external forces like friction, which might cause a change in momentum or an impulse. And let's go ahead and write those final. We don't know David's final velocity. And we know Sandra's final velocity is equal to positive 2.2 meters per second. All right. So total momentum is conserved, right? And that's kind of the idea here. I kind of want to go ahead and solve the problem before I answer these questions underneath. So I'm going to need another page here. Let's see if I can put a second page in. All right, let's see. How do I do this? I don't know why this is so difficult. I think I just go down here. Okay. Let's add a page. And I think we'll be good. So let's go ahead and write this momentum balance, right? So PI equals PF. We can say the momentum initial of David is going to be MV, right? And that's going to be V initial. So it's going to look like this. So for David, we have David's mass times the velocity of David initial. And then we're going to add that to the momentum initial of Sandra, which is Sandra's mass plus the velocity of Sandra initial. Set that equal to the mass of David times the velocity of David final. So this is David's final momentum right there. And we're going to add that to the mass of Sandra plus the velocity of Sandra, final. That's okay. The order doesn't matter of the subscripts. So what we have here is we have PI of David plus PI of Sandra equals PF of David plus PF of Sandra. So just so you can understand, that's kind of what we're saying here. So this is, I'll just write that this is PI David plus momentum of Sandra initial equals my P kind of looks like a D, the momentum of final of David plus the momentum final of Sandra. All right, that's kind of what we're saying here. So there's a couple ways to write it. I'm going to go ahead and plug it in, all the numbers in black that I know. The mass of David, we said was 80. The mass, or the velocity David initial is 0. Mass of Sandra is 45. Velocity of Sandra initial is 0. So yeah, it's the whole left side's going to equal 0. I realize that, but I just wanted to write it out and show you. Mass of David is 80 kilograms. We do not know David's final velocity, so we're going to solve for this. And we're going to add it to the mass of Sandra plus her final velocity, which is 2.2 meters per second. All right, so let's go ahead and simplify the left side. So this is just going to be 0. We'll set it equal to 80 times VDF plus 45 times 2.2 is 99 kg meters per second. All right, so we'll just add one of these to the other side. Maybe the 99, it doesn't matter, or subtract one of these to the other side. So we get 99 kg meters per second is equal to 80 times VDF. Divide both sides by 80. Cancel that away. And we're left with VDF is equal to a negative 99 over 80, which is negative 1.24 meters per second. Notice the kilograms canceled away over here too. Okay. So this is our final answer, right? And notice that in magnitude, right, it's smaller than the velocity of Sandra. I guess this makes sense because David's momentum or David's mass is larger. Signs are different. Obviously, if her momentum is to the right, then his should be to the left to balance it. But is total momentum conserved, and how does the system affect that? What if the system was different, right? And so if we go back up here, so it says, the first question says, if the system was Sandra only, would momentum be conserved? And so in this case, David would be an external force, right? The force from David. And so what we're seeing is when there's an external force, that momentum is not going to be conserved. Let's look at why that is. So if we look at Pi of Sandra, we see that it's not equal to the PF of Sandra. Why is that? Well, initially, Sandra had zero momentum, right? 45 times 0 for the initial, right? I can write that out. And finally, she had 45 kilograms times positive 2.2 meters per second. So we're seeing that 0 initial, right, does not equal 99. All right, and this is a positive 99. Okay, well, what about David, right? So before I move on, I guess the point I want to make here is that momentum is conserved if you make the system large enough. And if you don't make the system large enough, which we see right here, then momentum is not conserved. But in general, in the universe, momentum is always conserved, right? Because for any collision, it's always conserved if you draw the system appropriately. And so if the system was the universe itself, right, the system was so large, then momentum would be conserved. There would be no external forces. So I just want to point this out because this is a key idea, right? Because this could show up on the AP test where they're like, show how momentum is conserved in this collision. Show how momentum is not conserved in this collision. And you would have to draw the system differently, right? And if you make the system large enough, momentum will be conserved. If you don't, the momentum is not conserved. So let's look at David, right? So we're expecting for David that it's also not conserved. Whoops, I'm trying to write it the same way, so I'm not writing it differently every time. So Pi of David does not equal PF David. We see this because David's mass is 80. Initial velocity is 0. David's final mass is still 80, of course. His final velocity, we said, is, what was that, negative 1.24? Okay. And if we do the math here, this ends up equaling, you want to take a guess at that? Momentum is conserved. So what we're seeing is that it's going to end up equaling negative 99 kg meters per second. And so the next question says, what is true about the change in momentum of Sandra and David? Calculate the change for them both. If we want to find the change in momentum, let's just go ahead and do that like this. So for Sandra, it should be, oh, hey, what's up? I was just making a lecture. I can pause it, I think. Okay, so sorry about that. I was interrupted there for a second, and let's get back to it. So we can look at change in Sandra's momentum. We'll say PF Sandra minus PI Sandra is equal to 99 or positive 99 kg meters per second minus 0, right? Which is just going to be 99 positive. All right, and then we can say change in momentum for David is going to equal PF David minus PI David, which is equal to negative 99. You can see it's going kind of the same route as before, minus 0. And I really didn't need these formulas to see this, but a lot of times when you get asked about the change in something, just go ahead and use that delta formula and work off there. So we can see then that the reason momentum is conserved is not that the objects had 0 change in momentum, right? Which I think is sometimes what students focus on, right? It's that the momentum gained in one direction is equal to the momentum lost or gained in the other direction, I should say, by the other object. So we can see that momentum is conserved because Sandra gained positive 99 and David gained negative 99. And if we add those two together, we see that the total is 0. So the change in momentum total for the system would be 0, right? If we just add those two quantities together. And that's the idea of how momentum is conserved. So that's how it works. Anyways, I just wanted to bring that up. Something that also, I think this one makes sense to students, but if let's say they were moving, let's say the system, that they didn't start at rest, both of them, that they were moving together to the right, say, with 10 kilogram meters per second of momentum to the right, then at the end, the system would still have 10 kilogram meters per second momentum to the right. And that's a little trickier, right? Because I think this one makes sense to kids because it's 0 momentum initial and it's 0 momentum final. But that's not the idea, right? The idea is that the change is 0. So therefore, if it was 10 initial to the right momentum for the system, then the final would be 10 momentum to the right final. That's kind of the idea, that the change is 0 from initial to final, right? That's the bigger picture. That delta P total is 0. All right, so hopefully that makes sense. There is one more that I'm probably going to go ahead and do, and let's see how it goes. Okay, so it says Bob is running from the police and he thinks that he can make a faster getaway by jumping on a stationary cart in front of him. He runs towards the cart and jumps on it and rolls along the horizontal street. Bob has a mass of 75 kilograms. The cart has a mass of 25. If Bob's speed is 4 meters per second when he jumps into the cart, what is the cart's speed after Bob jumps on? All right, so let's go ahead and write this out. So we're saying that the mass of Bob before, let's see, so we'll draw it like this. We'll have Bob here running towards the cart. We'll have the getaway cart right here, just drawn like a skateboard. Let's see. So VI of Bob is going to equal 4.0 meters per second. Mass of the cart is equal to 25. mass of Bob, 75. And yeah, velocity initial of the cart, we can add that in too. That's going to equal 0. It's just sitting there. All right, so Bob is initially moving to the right, and okay. Then finally, Bob jumps on the cart. Bob and the cart head away and towards the right. And the question is, how fast? I'm going to go ahead and make the mass Bob plus the cart. So we'll just add them up. Give us 100 kilograms. And we can do this when two objects stick together like this in a inelastic collision, right? Where they're going to, they're going to be one object. Where they're going to be, you can think of them as one object because they have the same velocity. If you'd rather think of them as two objects with the same velocity, go right ahead. It still works. It's no big deal. Okay, so let's go ahead and do the calculation here. I think we got some space for it this time. Hopefully there's enough space here. PI equals PF. We're saying that the mass of Bob times velocity initial for Bob plus the mass of the cart times the velocity initial for the cart. And we're going to say is equal to VF Bob plus the cart, which we want to know, times the mass of Bob plus the cart. I noticed I did this one in the wrong order, where I usually have mass first, but that really doesn't matter in multiplication, right? 2 times 3 is the same as 3 times 2. Okay, so let's go ahead and plug in some numbers here. I'll just put this mass first now. I don't know why. I'm a stickler for that, but just trying to do it the same. Okay. So we can go ahead and see that this is going to go away. This is 0. 4 times 75, what's that, 300? So we're saying 300 kg meters per second is equal to 100 kilograms times VF B plus C. And if we divide both sides by 100, we get VF B plus C is equal to 3 meters per second. Notice it's positive or to the right, so looks like that is good. Is momentum conserved for this collision? The answer is always yes, right? Assuming you draw the system appropriately. Give an example of how momentum is conserved. Okay, so for this one, we can talk about, that the total momentum for the, or total change in momentum should be the same initial and final. So let's go ahead and do that. So what we can do is we can look back up at our the problem we just did. Let me see if I can get my highlighter going here. And we can see from our momentum balance, if we go up to this point right here where I just highlighted, right, that we have the momentum initial, right, of both objects is equal to the momentum final of both objects. And we can see that the momentum initial of both objects is equal to the momentum of just Bob, which is kilograms. Well, let me write that in there because I kind of want to see that. So what I'm saying is the momentum initial is just from Bob, because the cart isn't moving, right? And the momentum final is equal to, I can write it this way. Let's do it this way. And the momentum final is equal to momentum of Bob plus the cart final, right? This is what we're saying, how we're saying it's conserved. So if I add in the values here, let's see, this is going to be 0. This one is going to be 300. We can see that from up above in the yellow highlighted part. And the momentum of Bob plus the cart is going to be 100, right, kilograms, their total mass, times their final velocity, which is 3 meters per second. And this is going to equal 300 as well. So what we're saying then is the momentum of this entire system is conserved. So we can write that down in words if we want. The momentum of the system of Bob plus the cart is conserved. The idea being there are no external forces to cause an impulse. Remember, an impulse is a change in momentum. All right, so what kind of external force would cause an impulse here? Maybe friction. If we considered friction from the road, that could cause an impulse. But we're not considering that, right? Because the road is not part of the system, and we are just looking at the forces in the system. And if we did consider friction, then it would be an external force outside the system that would cause an impulse. Give an example of how momentum is not conserved. We can give 2 here, right? So we can say, we can do what we did up here, right? For David and Sandra. So we'll go ahead and say PI of Bob does not equal PF of Bob. The PI of Bob we just said is 300. What's the PF of just Bob? Well, it'd be Bob's mass of 75 times Bob's final velocity, which is 3 meters per second. And this would be, what is that, 225? Yeah. All right, and the reason we see this is because there is an external force coming from on Bob coming from the cart, right? So this is why that the Bob's momentum isn't conserved. If we do the same thing for the cart, all right, PI of the cart was 0. Whoops. Okay. PF of the cart, what was that? Well, that's 25 kilograms times that final velocity of 3 meters per second. It's going to equal 75. And that makes sense, but I thought I'd point this out, right? That this plus this is that 300, right? The cart's momentum plus Bob's momentum is 300. So what we're saying here then, if we look at what we did last time, which is the change in momentum of both, so delta P of Bob is equal to PF Bob minus PI Bob which is equal to what? PF of Bob was 225. PI of Bob was 300. It's equal to negative 75. All right. Okay, what about delta P of the cart? Now, if it was like last time, it should be positive 75, right? And I think that's what we're going to see. That the momentum changes for both objects are equal and opposite. And that goes along with the fact that the impulses on both objects are equal and opposite. And because the forces on both objects are equal and opposite according to Newton's third law. All right, so let's go ahead and solve this. PF of the cart is is 75. PI is 0. Oh boy. I don't know if I can erase just that. Let me try that. Yeah. All right. So what we're seeing is that the delta P total, once again, the total change, right, of the momentum in the system is equal to positive 75 plus negative 75. Oh, what happened to my other unit there? There we go. Which is equal to 0. So the total momentum is conserved. There's no total change in momentum of the system because there's no external forces causing an impulse. External forces cause an impulse, which changes the momentum of the system. And all forces are internal. All right. Cool. Hopefully this makes sense and you like the lecture. All right. Have a good day.